Thanks for coming to our presentation about ceramic membranes. Ceramics are not very common in New Zealand because the technology is largely unknown and the membranes are more expensive than polymeric membranes. But ceramic membranes have real benefits, and we believe they're going to be much more common in the future. Because Lutra wanted to gain first-hand experience with ceramic membranes and help introduce the technology to New Zealand, we bought a membrane skid and built a pilot plant around it. Together with Waipā District Council, we ran a trial on their Alpha Street water treatment plant in Cambridge and used the pilot plant to treat Waikato River water. In this presentation, we're going to share our experiences with the ceramic membranes and the results of the trial. And before we get started, I just want to point out Lutra doesn't sell ceramic membranes. We had some help, but this was an independent trial. In this presentation, we're going to cover what ceramic membranes are, the benefits of ceramic membranes, why they're interesting for New Zealand, our pilot plant setup, and plant performance. Ceramics are used for solid and liquid separation, similar to polymeric membranes. Ceramics can be used in most cases where polymerics are used, but the reverse is not true. I'm going to compare ceramics to polymeric membranes a couple of times in this presentation. I just want to point out I'm not trying to bag polymeric membranes. They provide high quality water. There's a huge body of knowledge around their performance, and they have their place in water treatment. But we'll point out some properties where ceramics are better. So ceramics are made of a ceramic material such as alumina or silicon carbide. They're hard, almost stone-like, and chemically inert. This makes them very durable, and they can be subjected to intense operational conditions and then frequently cleaned with high-strength chemicals without getting damaged. Polymerics, on the other hand, are made of a softer material, and care has to be taken during operation maintenance. The lifespan of a polymeric membrane is typically assumed to be 8 years, and for ceramics that's more like 15 or 20 years or even more. The second big advantage of ceramics are the higher flux rates. For example, in drinking water treatment, flux rates are 200 to 350 LMH. Polymeric usually operates between 50 and 100 LMH. This means less membrane area is needed to treat the same flow. This combination of durability and high flux means that ceramic membrane plants are smaller and need less membrane replacements. The image on the left shows a flat sheet membrane that's usually submerged in a water tank, and water is pulled through. This is the system that our pilot plant used. On the right side, you see tubular membranes, and they're often used in pressurized systems where the water is pushed through. Due to their hardy nature, ceramics are often used in industrial water and wastewater treatment, but they're also used in municipal water and wastewater treatment. Some examples of large-scale drinking water plants are the 120 MLD Andijk 3 plant in the Netherlands, or there's a 180 MLD plant in Singapore, Chao Chu Kang Waterworks. But there are many more installations worldwide, and their adoption rate is increasing. So the obvious question is, why are ceramics not more widely used? And the obvious answer is because of costs. Ceramics are more expensive to buy than polymeric membranes. But production costs have come down in recent years, and when looking at the full life cycle of a membrane plant that includes CapEx, yearly OpEx, and membrane replacements, we believe ceramics could now be competitive with polymeric membranes. So the reason why they're interesting for New Zealand is the same as globally. It makes economic sense. And more New Zealand specific and related to recent events, this is another kind of protozoa barrier that councils can use to comply with drinking water standard. Under the drinking water quality assurance rules, most drinking water suppliers serving 500 people or more must provide a 3 to 4 log removal protozoa barrier, and ceramics provide up to 4 log credits. They can be used under the treatment rules T1, T3, and T3, And the membrane rules apply for both ceramics and polymerics. This table shows some noteworthy T3 membrane filtration rules. The membranes must be certified to be NSF 61 and 419. We had silicon carbide membranes and they weren't certified, but there are alumina membranes with the same form factor which have this certification. Then a daily integrity test must be done. The filtrate turbidity must not exceed 1 NTU at any time, or 0.1 NTU for more than 15 minutes. Ceramics have the same performance parameters as polymeric membranes. I list some important ones here. The flux is the liters of treated water per membrane area per hour, or LMH. Then the flux at standard temperature, often 20 degrees. So temperature has a big influence on membrane performance because it influences the water's viscosity. So if a membrane pulls through 200 LMH at 10 degrees, for the same TMP, it could pull through 268 LMH at 20 degrees. Transmembrane pressure, or TMP, a higher flux results in a higher TMP, and a lower flux in a lower TMP, similar to all hydraulic systems. The specific flux is the standard temperature flux divided by the TMP, and that's used to compare membrane performance at different temperatures and different fluxes.
Kia ora koutou. To first go over our pilot plant, I will start at the main plant we were operating at, and this was our first street water treatment plant. That treatment plant has Packle coagulant dosing and inline mixing through the river pumps. This is then fed into two large clarifiers, and powdered activated carbon can be dosed for taste and odour. The flow is then treated through automated valveless gravity filters, and then has chlorination and UV treatment as well. On the screen behind me is images of our pilot plant setup. This was a containerized system using submerged flat sheet membranes. We had 3 modules of membranes for a total surface area of 18 square meters. We had 2 feed sources from the main water treatment plant, being the clarified water for commissioning last December, as well as that dosed raw water coming in. Our pilot operation was at around 200 LMH flux, with brief stints above that. Our ceramic membranes are silicon carbide, provided from a German company called Serafiltech, and have a pore size of 0.3 to 0.5 micron. Here on the screen is a simplified schematic of our pilot plant setup. We start with that feed supply from the main treatment plant and go through a raw water IBC. This water is then pumped into our filtration tank where the submerged membranes are kept. As Andreas mentioned, this is an out-in system, so the water is then pulled in through the membranes by the filtration pump into the permeate IBC. This permeate water is also used for backwashing the membranes. This is a reverse process, so it is in and out through the membranes, and that's to push off dirt and dislodge the solids. We occasionally drain during backwash to remove a buildup of solids in the tank. We have 3 ways to clean the system, and we use sodium hypochlorite and citric acid to do so. We can spray the chemicals on top of the ceramic membranes. We can add the chemicals into that backwash dose line, or we can shut the plant down and do a recovery soak, which is an overnight soaking of the membranes. On the screen you can see on the left-hand side is what one of the cassettes look like. As I mentioned, we have 3 of those cassette modules within our filtration tank. Lastly, for this side, I will state that we did not have pre-treatment within our pilot plant system. This was all done through the main water treatment plant. Lastly, to look at the pilot plant setup, we will go over some raw water conditions. So we were taking water from the Waikato River, which is shown by the turbidities on the screen, is a bit weird for a river water, being that it is generally low turbidity. At the end of January, we did have a spike from the Auckland anniversary flooding events. There was typical pH and conductivity for the river water. Temperature was another variable that changed in wet conditions. This acted naturally over the seasons and got colder in winter. This is an interesting parameter that affects the flux rates that we see in our results next.
Let's have a look at some results. First, I want to mention the filter turbidity. We had an Anderson-Hauser Turbimax sensor on the permeate line. And being a pilot plant, we had some air issues in the beginning, but after we sorted that out, we had consistent turbidities at less than 0.04 NTU, which is compliant with the drinking water standard. I won't be showing turbidity results going forward, but just keep that in mind. Flux rates. So at the start of the trial, we're just getting familiar with the plant, and we hadn't automated the chemical cleans yet, and so we operated without them. So this is not how a ceramics plant would normally be operated. Just keep that in mind as well. We started with clarified water with low turbidity. This allowed us to experiment with fluxes between 300 and 400 LMH. I'll quickly explain this graph because you're going to see it again. The top shows the flux in LMH, and the gray bars indicate when we did operational set point changes. So you see at the end, we ramped it up from 300 to around 400 for a couple of days before Christmas. The second graph shows the specific flux, and the third graph shows the TMP. So we can see how the TMP, the specific flux, is useful. As we jump from 300 to 400 LMH, the TMP drops, but the specific flux more or less stays the same. And that's why it's useful to compare membranes. We ended up running the plant mostly around 200 LMH. We know of a drinking plant in Australia that with the same membranes that runs at 250 to 300 LMH. And this shows the high flux rates that ceramics can be operated at. One of the objectives of the trial was to find sustainable parameters for operation. And by sustainable, I mean that the specific flux remains constant. This graph shows the time from April to June, and the green shaded areas indicate when we found stable operating parameters. As you can see from the gray dotted lines in the top graph, we made a lot of operational changes, and we tried out different combinations. And even when we had operated sustainably for a while, we changed some parameters to see if we could increase the performance. That's why there are not more green areas here in this graph. In this period, we operated on raw water that was dosed with PECO and relied on inline mixing for coagulation and flocculation. This table shows some sustainable operational parameters or combinations of them. So the flux is between 200 and 220. Filtration length was 30 to 15 minutes. And one of the key takeaways for us is that ceramic membranes need more frequent chemical washes than polymeric membranes. We had to do it around every 3 hours. We spoke to operators and suppliers of ceramic membranes, and typically a chemical wash is done every 12 hours or once a day. We think the reason for this difference is the lack of optimized pretreatment at the Alpha Street plant. And by that I mean processes like pH correction, coagulation, or flocculation. As mentioned, our pilot plant didn't have any pretreatment capabilities, so relying on Alpha Street for the water. And this was confirmed by the ceramic supplier. They did a bench scale test of Alpha Street raw water, and based on these results, they would design a full-scale plant with chemical washes every 12 hours. That test also showed that it could be run with flux rates about 250 LMH. Let's talk about performance outcomes. I've mentioned filter turbidity already. Production efficiency, and by that I mean the fraction of the water that goes into supply compared to what has been extracted from the environment. Our pilot plant didn't have a backwash recovery system. Full-scale plants have. They usually operate with 90% efficiency or more, which means that 10% of the water is lost in the sludge treatment and 90% is returned to the head of the plant. So if we assume a conservative recovery efficiency of 80%, then our pilot plant operated at an overall efficiency of 95% or more, and that's a good value. The chemical consumption, we measured that as well. These numbers won't mean that much. So to put them into context, If you scale this up to a 6.5 MLD plant, the chemical cost would be around $18,000 a year. And out of an annual operational budget of several hundred thousands. So that cost is not that significant. So this difference between the pilot plant results and the full-scale plant, as I said before, is down to pretreatment. Pretreatment is really important. And what does it mean if you buy a ceramic membrane plant? Or any plant, in fact. It means that the supplier needs to provide performance guarantees and define or provide the pretreatment. And we need good raw water quality data to provide to the supplier. This is obviously not revolutionary. It's common sense and what is usually done when people buy membrane plants.
An interesting moment during the operation of our pilot plant is this event dubbed sludge apocalypse. If you can look on the graph at the TMP, we start at about 250 millibar. Over the weekend period, that decreases quite rapidly. And that occurred due to a human error where the drain function was not activated. So the plant was accumulating solids within the tank without draining them. And you can see with the image, we got a very concentrated sludge. The blue line on the graph is when I intervened and got a garden hose out to wash, fluidize, and drain the solids from the system. Fortunately, that worked. This sludge apocalypse was not a death sentence to our pilot plant. I did not need to take the membranes apart and desludge them separately. This is important. In wastewater applications, you typically have to decompress the cassette and manually clean the panels, which I did not need to do here. The green line on the graph, after my intervention, we still had that decrease in TMP. That suggests I was fully able to remove the solids from the filtration tank, which is when we did a recovery wash with that green line on the graph. So recovery soaks are quite an important part of membrane operation. They are done infrequently when organic or inorganic fouling is accumulating on the membranes that can't be removed through those normal backwash operation periods. We did a few of those during our pilot plant operation because we were tweaking parameters and making the pilot somewhat dirty along the way. What it shows is that during the sludge apocalypse event, we did not damage the membranes and we were able to recover the efficiency and operational conditions for the later months that we kept operating. While we operated our pilot plant for a short period of time, we've also spoken to someone over in New South Wales who has operated the plant for 18 months. This was Doug from New South Wales. Doug has 20 years experience in membrane filtration and his plant is 35 cube per day, so relatively small. Their water is groundwater, which is then kept in a pond for about a year before treatment. The NTU sits between 10 to 20 NTU with high peak events at about 90 NTU, and there are algal plumes in the pond. Doug operates his plant between 250 and 300 LMH. In his own words, he finds the system incredibly robust and he had no problem after a PACL overdose to get that recovery back and operate normally. He's found it an automatic system, which is easy to use, and he very much enjoys the ceramic membranes. If he could choose, he would keep using them as long as he can.
This brings us to quick conclusions. The ceramics met the turbidity requirements of the drinking water standard. There is an aluminum membrane with the same form factor that has the NSF certification. The ceramics we found them to be durable, and we could restore them even after intense sludging. We don't have first-hand experience of the full life cycle of a membrane plant, but our experience seems consistent with industry experience that ceramics need few, if any, replacements. We ran at a flux rate of 200 LMH, and this combination of durability and high flux, and considering the whole of life costs, we think that ceramics are economically competitive with polymeric membranes. We did a high-level net present value NPV calculation, which showed that ceramics are slightly cheaper than polymeric membranes. This gives councils another option to comply with drinking water standards. And like with any membrane plant, the supplier needs to provide performance guarantees and defines or provide the pretreatment.
Lastly, we would like to acknowledge White Bar District Council, particularly David Luke and David Kennington, for their support during the pilot plant operation, as well as Infinite Water, who provided us with that knowledge about ceramic membranes and tweaking our parameters. Thank you.
Thank you.
A few questions?
I'm not sure if it needs it. I think if it's needed, the supplier would provide it. But in terms of like heat resistancy, the membranes can be subjected to up to 800 degrees, so it wouldn't be an issue.
I guess as well, because they're ceramic membranes, they can sustain higher concentrations of chemicals in the washes, and I believe that's what helps them and not always need that hot water.
Well, they are sort of stone-like materials. If you drop a hammer on them, they will break, but otherwise they're very robust. I guess you pack them good and protect them, and then they should last a very long time.
In terms of the pre-treatment, I guess it was a starting operation for us, so we were still finding what we needed or what we didn't, and we figured it would be interesting results to get it straight from the river.
Yeah, so this was a microfiltration, but it can take out, depending on the pre-treatment, it can take out dissolved organic carbons, algae, turbidity, organics, so really depends on the pre-treatment. So you could dose powdered activated carbon in front of it and use that to get rid of taste and odor and the cyanobacteria.
So yeah, it would be possible.